Hello and welcome to NPTEL online certification course on microelectronics devices to circuits. In our previous lecture we had discussed with you the pi model and the T model. We have also discussed with you the condition for small signal model, and we have seen that the requirement for small signal has been that if your input signal is small enough so that your bias point does not change too much and you are in the linear region of operation of the device where amplification is almost independent of the input voltage, we define that to be as a small signal. We have also understood that if I have a BJT in a common emitter configuration, then the amplification is typically very large, of the order of few hundreds in voltage amplification, whereas common collector does not give me voltage amplification directly, right. We also understood about the relationship between alpha and beta, where beta is basically the current gain and alpha is also a current gain in common emitter configuration, and beta is common current gain in common emitter configuration, and alpha is the current gain in common base configuration. We have seen the functionality and the operation of BJT. What we will do today is have a look at small signal circuit model. We will extend that to CE, CB and CC, which means common emitter, common base and common collector. So, just to continue with yesterday's talk, we will come to this point that if you have a common emitter configuration which you see, then as I discussed with you in the yesterday's discussion or slide, that you do have a BJT here which is an NPN transistor. Looking at the direction of the arrow, this is basically an NPN, right. So, I have a p type base and e type emitter, and we have got a collector which is n type. There is also a resistance RC, which primarily is a resistance which is seen at the collector side, right, and you have an input resistance also referred to as RSIG here, and we define R in as the input resistance or input impedance and R naught as the output resistance or impedance, and V naught as the output voltage, whereas V sig is my input voltage. Now, you see the two aspects which should be very clear at this stage, that V sig is not equal to Vi, right. So, your input voltage to the BJT will be slightly less as compared to the actual signal voltage, and the reason being the presence of this R signal, right, because these are all voltage sources, right, and these voltage sources will have a finite output impedance, and as a result this output impedance there will be some drop across that output impedance, and therefore the actual potential applied to the base emitter junction of a BJT will be relatively smaller than what is expected from here, right. Now, so we have therefore, if you so this BJT is broken up into equivalent small signal model, as you can see the blue box here, where you have R pi is basically nothing but the value of R in, and the reason being R pi is nothing but the resistance between the base emitter junction, right. So, when the base emitter junction is forward biased, this R pi will be of the order of few ohms, right, the order of ohms, right, because it is a forward bias device characteristics. Now, so the voltage across this R pi is the voltage which is basically VBE, happens to be V pi. So, V pi is the voltage across R pi, right. So, this is sort of an input voltage which is visible to us, and that when multiplied by transconductance Gm gives me the output current, right, and that is the current. So, Gm times R pi or V pi is my output current, that if you multiply with the effective resistance seen from the output side. What is the effective resistance? RC parallel to R0, right, RC parallel to R0, and therefore I get V0 equals to minus Gm times Vi into RC parallel to R0. So, if you look very carefully or understand it, then it is basically minus Gm times V pi, right, RC parallel to R0. This is the value of your V0, right. So, if you break it down, Vm pi, this will be RC R0 upon RC plus R0, right. This will be your so basically 1 upon this, so minus GM V pi into R0 fine. So you see, therefore, this, if you break it up, I get 1 by R0 plus 1 by RC, right. This is equals to your V0 for all practical purposes. Now you see where R0 and RC is the external potential or RC is the external bias which you have given, and R0 is the basically the output impedance of the BJT, right. So the parallel combination of R0 and RC gives you the net output impedance seen by the device, and therefore I have written here that R0 is equal to RC parallel R0, right, and that gives you a fair idea about the type of voltages which you will get. Since GM is relatively high, right, so GM is high, even if this quantity is low quantity, right, even if it is low, I will get V0 which is quite high, right. So therefore we can safely assume that that the gain is directly proportional to GM, which is an understood phenomena, that it is actually depending on the value of GM. So higher the sensitivity is for a BJT to work, more will be the gain, and therefore more will be the output voltage for the same amount of input voltage. But please keep in mind that the V sig which you are using, or signal input signal voltage, is basically a small signal, right. Please keep this in mind for all practical purposes. This is basically small signal, right, and therefore these are all small signal models. Now if your signal is large, then you entail a nonlinearity into your GM. So assuming GM to be constant will be an over assumption, right. So one important point when you do a nonlinear analysis or a nonlinear profiling, right, which we are not doing here, nonlinear, then GM will be actually a function of V in this case V pi, right. But in reality, or at least for the all understanding purposes, basic purposes, we assume that GM is sort of independent of V in, right. In reality, GM might be also a function of V pi, and therefore you will entail a nonlinearity into the whole system. So therefore we have understood that you do have a problem of a nonlinearity also coming into picture, but if we sustain a small value of input voltage, there will be no nonlinearity, and I would expect to see a gain which is totally independent of V in, and a linear gain will be available. Two things we therefore the take out from this slide is that my input impedance is R pi and output impedance is basically RC parallel to R0, right. Now so your input impedance is basically R pi, which is nothing but the forward biased EBJ, right, emitter base junction. The resistance offered by that is basically my EBJ, right. Second thing is, there is also assumption that this is behaving like a constant current source, right, constant current source, and we are also assuming it to be ideal. So the voltage, so the impedance offered by this is infinity, but since this is in parallel, of course, therefore this does not play into picture. I think it is clear to you, right. So what we have therefore assumed is that the current source is basically an ideal current source. As a result, the output impedance is infinity. Since it is a constant current source and the output impedance is infinity, when it is in parallel to R0 and RC, right, so that vanishes off because it is quite high a quantity, right. So in parallel combination that does not stay to a larger extent, right, it is always less, because in parallel you remember is less than the least, in series it is larger than the largest. In this case it is less than the least, and therefore we just neglect that particular case, right. Okay. We then move to the next slide and see what happens with emitter resistance. Let me see, why do we at all need an emitter resistance? Very, very important issue is there when we have an emitter. Till now, if you remember, we were actually looking from the point of view of the fact that we had a BJT, right, and there was a resistance here, fine, and you had a bias here, and this bias was varying, and you did it like this, then like this, and then we have plus VCC, and then we are doing like this, sorry, we are doing like this, is RE. Now what we are trying to tell you is that no, let me do small a change here, and the change is that we try to do some change in emitter configuration. And what is the change? Change is that we try to put a resistance here. Why we will see that later on. So, let me put a resistance Re here, right, emitter resistance. All right. Now, see the reason we want to do it is to ensure what is known as stability, ensure stability of the circuit, and I will explain to you how do I get it. See, if you remember from your basic class 10th, even undergraduate days, that or you can understand that whenever you have a negative feedback, right, whenever you have a negative feedback, you automatically have a more stable system, right. The price you pay for it is the gain starts to fall down, right. So, if I do a negative feedback in voltage domain, which means that the output feedback, output voltage is fed into the input voltage side with a 180-degree phase shifted value, then I can safely assume that my overall gain will reduce, because obviously there will be principle of superposition can be applied and the two voltages will be added algebraically. As a result, the overall voltage might fall down, but then we also ensure that by doing a negative feedback that the overall gain is more stabilized, which means that the gain with respect to change in the input is much smaller. So, negative feedbacks actually gives you a stable system. That is what we have learned, and we know, all of us possibly know this basic concept. Now, if this Re is in series to this external emitter resistance is applied to the side of emitter, then when a current IE flows through it, then there is a voltage drop which is IE times Re, in which this is positive and this is negative, right. So, the voltage across this, which is, let us suppose we assume it to be as VE, appears because of IE Re, right. This VE will start to reverse bias my this base emitter junction, right. So, as it starts to reverse bias it, because why? Because you are applying positive side to N type and maybe a negative side to P type, fine, or even a positive bias to the N side, and as a result what is happening is that the emitter is getting more and more positive, which means it is trying to reverse bias the emitter base junction, and therefore a majority current carrier is reducing and you have a large amount of minority current carrier which appears. Therefore, when you apply Re, your gain starts to fall down, right, and it starts to go down and down. So, when you put a emitter resistance Re in series to the BJT, we end up having a reduced gain, right, a reduced gain, but a more stabilized circuit. So, I have a reduced gain, but more stabilized circuit is with me, right. So, that is the reason why we do why we bias with emitter resistance. Now, if you look very carefully, therefore, in this case we have an Re here, which is basically this one, and therefore, Rin is given as beta plus 1 Re plus small re plus capital Re, right, where capital Re is basically the resistance, external resistance, and Re is the internal resistance. So, if you go from this point to this point, it is basically Re plus Re which you see in front of you, right. That you multiply with beta plus 1, you get total Rin value, right, because that is the basic definition of a beta. Now, beta will be much larger than 1, and therefore, I can safely write down Rin to be equals to beta times Re plus Re, which appears as beta Re plus beta times Re, right. So, if your beta is typically very high, let us say it is about 150, 200, then the resistances offered by the BJT, right, and the circuitry gets amplified drastically, right, and the input resistance becomes very large, because you can see here you are multiplying beta to both Re, small re and capital Re, and as a result you will have a large amount of voltage across this terminal, right. Not only that, you will also have to reduce the gain of the MOS device which you are using, or the FET device, or the MOSFET which BJT which you are using here. Now, therefore, I get AV 0 to be equals to minus GM times RC divided by 1 plus GM RE, right. So, it is basically gain is equals to minus GM RC divided by 1 plus GM times RO, fine, and this is your voltage gain AV0. We also assume for all practical purposes that RE is so large as compared to RC that RC is approximately equals to RE, and as a result R0 equals to RC, right. So, the output impedance or the output resistance seen by the device is approximately equal to the collector resistance offered by the BJT, right. This two things we will be assuming for all practical purposes. If this is true, we can look at the left hand side figure, the down figure here, then we see that I have got V sig, I have got R sig, which is the signal specifications, which terminates at this particular point, and you have alpha times IE as the collector current source, right. Assuming that the emitter current is fully biased and only depends upon the input bias and not on anything else, I can safely say that the collector current here is equals to alpha times IE, right. The IE also flows to the below side. So, IE times RE is basically the voltage drop which you see on the below side of the channel, right, and that is what you get from all these regions, right. Okay. We now come to the common base amplifier. In the common base amplifier, you will see that my base is grounded, right. So, the previous was basically your base emitter grounded. Now, we are entering into base grounded. So, when the base is grounded, I am applying signal to the input side on the emitter side, and let us see how it works out. The problem with this is technically is when you apply a signal on the emitter side, right, when you apply a signal on the emitter side, you end up having a large parasitic capacitances being extracted even at relatively small voltages, right. And as a result, what will happen is that the speed of the operation will get reduced, right. So, one has to be very cautious when we design a common base amplifier in a small confined domain. Now, with this knowledge we can safely write down, or we can actually give an instruction that R in is equals to RE, no doubt because of the previous discussion we can just remove it. So, if you see R in equals to RE, which is given here. So, I get R in equals to RE, that is what you get, R in equals to RE. Why? Because input resistance, right, input resistance which you feed here is exactly equals to RE. RE is the output impedance of a BJT at this stage. So, I get AV0 to be equals to GM times RC and R0 equals to RC, right. So, you can understand that your R0 is typically very large quantity, and therefore, GM times RC is very large, and that is the reason you do have a large amplification in their case, in their this thing, as compared to other experiments or other this thing, because the same reason is that your GM is relatively independent of the applied currents, right. Common collector amplifier, as the name suggests, it is also referred to as common emitter or emitter follower amplifier, and is given by this formula. In this case, please understand the voltage gain is approximately equals to 0, and that is what we all understand, that common collector is not a very good amplifier, or it cannot amplify small signal to large values, right, and that is quite important that they cannot do it. And since they cannot do it, they are used for some other purposes, but not for amplification purposes, right, and that is what we come to know, right, because AV0 equals to 1. So, it is basically phase change which is looking into, and nothing else than that, right, and it is given by alpha times IE, which is basically the actual current source which is available to us. RL is already there, R signal and V signal is also available, output impedance of current and resistances are also available with me, and gives me quite an interesting result as far as common collector or common this is given. So, let me recapitulate what we did. Common emitter configuration is the most easiest and the most high gain can be obtained from common emitter configuration. The common base amplifier use a high frequency amplifier at a low input signal, right. So, input signal is quite low, and therefore, you use a high amplifier design. The emitter follower finds application as a voltage buffer, right, for collecting a high source and pass it on to the right source. So, if you do a common collector, you are actually though your amplification will be low voltage to voltage, but your transits will be very fast, which means that if you want to compare the output impedance of a particular system with your system, on the collector side, if you put the resistance is small, and therefore you can easily match the low input impedance design. So, the emitter follower finds application as voltage buffer for connecting a high source to a low resistance source, right. So, emitter follower generally typically used for the purpose of buffering or the purpose of connecting between 2 points through a network, right, and that is what is emitter follower is all about. It is basically we require the power to be low and it is excessively low, right, and that is very important. With this we have almost finished this section, but before we move forward, let me give you a brief questionnaire or a question maybe, right. So, I have a question. So, I have a transistor whose beta is equals to 100, right, and applied voltage is 10 volts. So, I get IC. So, I need to find out first of all beta, this is 3 volts. So, I need to find out IB first. So, to do that, in this loop let me find out that this is 0.7, right, you are given 3 volts. So, what you get from here is that IB will be equals to VBB minus V, right, this drop divided by R, which is 100K, and if you solve it comes out to 0.023 milliampere, right. So, the amount of current which one flows is typically very small. So, therefore, IC will be equals to 100 times 0.023 milliamps. So, IC will be there for approximately 23 milliamps, fine. So, it is typically this much amount of current will be required for all practical purposes. Now, if you again go back and explain the relative slides here, we can safely show that that VC is equals to VCC minus ICRC, right. In this case, we find out this to be as plus 3.1 volt. Now, if you want to find out the value of RE, it is VT by IE. VT is 25 millivolt per decade divided by VT is divided by IE. Actually, IE will be VT divided by 99, and this comes out to be approximately equals to 10.8 hours, which means that 10.8 ohm is the emitter resistance offered by the emitter to the input system, right. Transconductance GM can be written as IC by VT, and therefore, this can be written as 92 milliampere per voltage minus, right. R pi beta by GM, we get 100 by 92 kilo, right. So, this is how we do a small signal analysis as far as this course is concerned, and gives you an idea about how a small signal analysis works even for a single transistor or for a BJT a transistor, wherein BJT starts to find out new methodologies to destabilize itself, right, and therefore, these are the few areas which people are working, and quite interesting work is going on. Now, so what we did was we used a common emitter configuration for the best configuration, and then what we saw was that for if your gain is typically very large, bulk gain is very large, and your actual gain of the device gain is relatively small, we can still have that as the best suited amplifier. The common base is used for high frequency, due to low input resistance. It is generally used for high frequency amplifier, right. The emitter follower finds application as a voltage buffer for connecting a high source to a low resistance path, right, and this we have done for emitter follower we have done, and we did for common base as well, right. We will therefore at this stage recapitulate what we did. We did emitter common emitter based configuration. We also looked into the fact that given a result or given this thing, which one is the best form of configuration, and for that common emitter is the best form of configuration as far as the results are concerned. Fine. Thank you very much for your patient hearing. We will come back to you next time with more information. Thank you.